This is going to be an introduction to the lambda calculus. So before you continue, please make sure that you have studied tree-based abstract syntax, operational semantics, and type systems, as we depend on these topics for the treatment of lambda calculus. Okay, here are some simple lambda expressions. So you could think of the lambda calculus as a very simple functional programming language for the moment. So for example, this is how we would define the identity function in the lambda calculus. So this is an expression. It denotes a function. It's actually a lambda abstraction. So in this manner we say, okay, we parameterize in some argument x and pass the dot. This is essentially the body of the function. So we return x. And therefore this is the anonymous, the unnamed identity function. Or here we've got a function with three arguments, f, g, and x, and we apply g to x and then f. So this is obviously the anonymous representation of function composition. So we have variable reference in the body, we have lambda abstraction to basically bind an argument. Well, and of course we have function application, g applied to x, f applied to g. So in this manner, with these three constructs, you can see that this is essentially a very simple functional programming language. So here maybe another attempt at motivating, at clarifying what the lambda calculus is. So it is obviously some sort of core of functional programming. In fact, it's also a Turing complete notion of computability, which means everything that can be computed can also be computed within the lambda calculus. It's actually a nice example of a calculus. I mean, something like a really fundamental core tiny language that may be used in other language designs. And indeed, it's a very popular calculus in programming language theory. When people explore new constructs or the type system thereof, then they often start from a lambda calculus. So by the way, the functional programming language Haskell is based on the lambda calculus. We see this, for example, we can define the identity function indeed as a lambda abstraction, so we don't use dot here, we use the arrow, okay? Or here we can define the function composition combinator also as a lambda abstraction. So we can apply the identity function, we can apply function composition, and everything works. Of course, Haskell is a much richer language, but at least it also contains the lambda calculus. So here's the semantics of the lambda calculus. Well, I mean, one can define the semantics in different ways. We focus on what's called the call by value semantics, which means that argument expressions of function applications are reduced before these arguments are passed into the functions. Also, we use small step operational semantics style in this definition here. The semantics is pretty straightforward. So we have this case here for function application where we essentially work on the function position of function application. So we make one step. And here we assume that the function position is already in value form. So therefore we try to make a step on the argument position. And here we assume that basically both components of the function application are in value form. So the first one has to be, in fact, a lambda abstraction, a function, and the second one, some value v. And now we use what's called substitution. So we replace the argument name x within e by the value v. And in order to have this distinction between expressions in general and values in particular, we assume an auxiliary judgment here to test that an expression is in value form, and in fact only lambda abstractions are in value form. Now we should actually explain substitution that we were using a little bit more in detail. And for substitution, we also need the notion of free variables in lambda expressions. Okay, so let's first look at substitution here. So this is about replacing a variable within an expression by some other expression or possibly a value. So here we want to replace x by e within the expression x. Well, so we just return e. Here we want to replace x by e in the variable y. So y, if it's different from x, we just keep it. Well, when we apply substitution to a function application, we basically just need to push substitution in both operands. When we apply substitution to a lambda abstraction, where the variable of the lambda abstraction is the same variable as we want to replace, well, then actually stop drilling into the term, because x is newly bound in this lambda abstraction, so it's no longer the same x as we face here. So this is the case for lambda abstraction where the variable of the lambda abstraction is not the variable that we want to replace. So in this case, we essentially can drill into the body of the lambda abstraction and continue with substitution. However, we need to impose an important constraint here, because we need to require that the variable y of the lambda abstraction is not free in the expression e, because if you would allow this, then the free variable of e would be captured by this binding here. So we rule this out by this constraint. And here is the very simple definition of what it means for a variable to be free in an expression. Well, obviously, when we have the expression x, then the variable x is free in that expression. When we have a function application, then variables free in either operand are free in the function application. And when we have a lambda abstraction, then all the variables of the body of the lambda abstraction are free except for the variable that is bound by the lambda abstraction. Okay, so now let's make our lambda calculus a little bit more convenient. So we're going to add some expression forms: true, false, zero, successor, predecessor, test for zero, and ifs and else. So we're going to add them. So these are just nice, well-known expression forms that we want to use on top of lambda abstraction, function application, and verbal reference. Okay, so if we had all these constructs, then we could start to define nice, well-known functions. Well, let's also assume for a moment that we had recursion. So if we had recursion, we could define addition in terms of successor function, and we could define multiplication in terms of repeated addition, and we could define factorial in terms of repeated multiplication. So these would just be primitively recursive functions, and in this manner we would be able to do useful things with this extended lambda calculus. Well, the problem is, of course, that we don't really have self-reference in a lambda calculus. We can give names to arguments, but we cannot define functions that can reference themselves. So we are a little bit in trouble. What we do is we introduce yet another construct, a fixed point combinator construct. So we basically revise the definition of add, mul, and factorial. So these are now just plain lambda expressions. So they are all parameterized by an additional argument f here, which is basically a proxy for the self-reference. And then we apply the fixed point combinator to it. So the idea is that the fixed point of a lambda abstraction is basically that we apply the body of the lambda abstraction and we replace the argument of the lambda abstraction again by the fixed point. So in this way we simulate recursion. And the other rule here is just for reducing the argument of fix until it's in value form. So this is a clever trick to add recursion by assuming an additional construct for a fixed point combinator. Well, it actually turns out that we don't need to do all these things that we have done, like adding true, false, if, and also fix. We don't need to add them because the basic lambda calculus with just the three constructs that we have seen, verbal reference, lambda abstraction, function application, just that basic lambda calculus is sufficient to encode all these other things. So that's maybe not that easy to understand, but here's the idea. So for example, we encode true as a function which takes two arguments, and we just return the first argument. For false, then we return the second argument, and then there's also some encoding of if. Or for the natural numbers, we just encode them by lambda abstractions that take an s and then a z. S, think of successor, z 0, and then the natural number n is encoded as a lambda abstraction where we apply s n times to z. So, which means we can really encode if and true and false and all the natural numbers. And here's also the encoding of the successor function, which essentially encodes s one more time. Well, and here is how we can even represent a fixed point combinator within the lambda calculus. And of course, this is now entirely non-straightforward to understand that this lambda abstraction has the right semantics. Maybe it helps you to realize that there's some copying behavior going on here, that this expression sort of is copying itself and applying itself time and again. This lambda term essentially behaves as our earlier fixed point combinator that was explicitly added to the semantics. And again, this is not straightforward, so this is just to show you that indeed the basic lambda calculus is Turing complete. Now we can actually implement, of course, the lambda calculus in a functional language. That is, we basically take the operational semantics. In this case, we assume that we also implement fix. And so we implement the operational semantics, let's say in Haskell, and then we can play with addition here. So here we have the addition function, and we use some convenience functions that map Haskell ints into lambda calculus expressions, and also lambda calculus expressions back into Haskell ints, so that we can look at real numbers and not complicated terms of the form suck something 0. So what we do here is we apply the add function to 20 and 22, and then we apply the steps function, which is the reflexive transitive closure of the small step operational semantics of the lambda calculus, and obviously we should get 42 as a result. We can also define a type system for the lambda calculus, and then we in fact call it the simply typed lambda calculus. So the typing judgment is going to use an extra typing context, gamma, which basically keeps track of types of variables. The syntax is a little bit extended insofar that lambda abstractions now carry type annotations. So the bound variable x also declares the corresponding argument type. So let's look at the typing rules one by one. So the first typing rule deals with the type of a variable. So x is of type t if the type context gamma indeed assigns t to x. So here's the typing rule for function application. The type of a function application is some type T2, if we can show that the function position E1 is of a function type, where T2 of course shows up in the result position, and now the argument E2 of the function application needs to be of the suitable argument type T1 that we already used here. The type of a lambda abstraction is of course a function type, because a lambda abstraction is a function, and it's a function type with the argument type being the type as declared by the annotation T1, and the result type is some type T2, namely the type of the body of the lambda abstraction. However, we need to adjust the typing context for checking the type of the body. That is, we need to assign the type T1 to the variable x within the body E. And we can also realize this typed lambda calculus easily. This would be then just like we always implement typing rules in a functional language, just as much as we can implement operational semantics definitions in a functional language. So here's the revised syntax in Haskell. So we have lambda abstractions with type annotations. This is the add function again. And here we invoke the typing judgment in Haskell, type of the addition function for an empty context. So what is the type of the addition function? It is basically a function type from not type to a function type, from not type to not type. So it's basically a binary operator on natural numbers, obviously. And by the way, we can of course translate the simply typed lambda calculus in the untyped lambda calculus. This is also called type erasure, that we remove type annotations. So verbal references just go to verbal references, function applications just go to function applications, and lambda abstractions with type annotations go to lambda abstractions without type annotations. So in this manner we will be able to use the semantics of the basic untyped lambda calculus even for the simply typed lambda calculus. So we would be using type annotations only to reject lambda abstractions statically that we don't like, but we wouldn't use type annotations at runtime, so to say. That's it. That was a very quick introduction to the lambda calculus, and there's more in the software languages book. And the two realizations here, like the untyped lambda language and the typed lambda language, their Haskell implementations are available in the YAS repository. Thank you.